The eastern Snake River Plain is underlain by silicic and mafic volcanic rocks, interbedded with sedimentary rocks. In the East Snake River Plain, we have 4 rock samples. The first, claystone, which is a sedimentary rock. Next, we have tuff, which is an igneous rock. Then we have basalt, which is also an igneous rock. And last of the rocks in the East Snake River Plain, we have siltstone, which is a sedimentary rock. The rocks that occupy the West Snake River Plain are rhyolitic tuffs and ash flows of the Idavantic volcanic group and fluvial and lacustrine sediments with interbedded basalt flows of the Idaho group. In the Western Snake River Plain, we have 5 different rock samples. First, we have the quartz sandstone, which is a sedimentary rock. Next, we have the volcanic conglomerate rock, which is also sedimentary. Then we have oolitic limestone, which is a sedimentary rock. Then we have the leaf fossil, which is a fossil. And the last of the samples for the West Snake River Plain is chert, which is a sedimentary rock. For Yellowstone, the primary ages of rocks are 2 million years old to 0.06 million years old. This is in the Quaternary period and the Pleistocene epoch. The primary ages of rocks for the East Snake River Plain. The rocks are 10 million years to 6.2 million years old. This is also the Tertiary period in the Miocene epoch.
Crazy.
The primary ages of rocks in the West Snake River Plain and what the ages are based upon. In the West Snake River Plain, there are rhyolitic tuffs and ash flows. They range from 15 to 11 million years in age. This is the Tertiary period and the Miocene epoch.
Now we're going to look at a general overview. The Snake River Plain is a basin bounded by faults, and the land surface and rock layers both dip toward the plain's axis, with large rhyolite domes nearby over the basalt. For size, it is about 20 to 43 miles wide, and it trends in northwesterly direction. The western and central parts of the plain are a downfaulted block that is somewhat like a graben. By the way, a graben is a block of crust that is dropped down. This usually is a result of extension of the crust. Moving on, downfaulting is the most significant geologic structure of the eastern plain, and the central and western plains continue to subside. Also, under the entire Snake River Plain is a 25-mile thick crust, which is much thicker than normal for crust. Now to talk about some major geologic structures. First, the Idaho silicic volcanics. They are between 9 and 14 million years old and are from the Miocene age. The oldest flows can be found in the western Snake River Plain, and then they get younger the further to the east you go. The silicic rocks from these flows are mostly welded ash flow tuffs, but there are also lava flows and vitric tuffs. Island Park caldera is also the biggest symmetrical caldera on Earth at 18 to 23 miles in diameter. Its southwestern rim crest is about 1,200 feet higher than the plain that is south of the caldera. Flow tuff constitutes most of its rock makeup. For tensional fractures, the Great Rift includes the craters of the Moon lava fields and is one of the most notable fractures in the eastern plain. And for fissure flows, the youngest fissure flows are at Kings Bowl and craters of the Moon lava fields. although Craters of the Moon covers almost 600 square miles, whereas King's Bowl only covers about a single square mile. And lastly, Shoshone Ice Cave covers about 85 square miles and is part of a complex lava system with much of the roof collapsed. Now for the general geologic history of the Snake River Plain. First of all, there are several hypotheses for the origin. First is extension to the north combined with crustal thinning. The second is a continent migrated over a hot spot that's now in Yellowstone National Park at the rate of about 1 or 2 inches a year. The third is crystal fractured from west to east. And the fourth is passive deformation. But generally, the hotspot model is the most widely accepted model, and there are 3 primary pieces of evidence to back it up. The first is, to quote from the Digital Geology of Idaho website, the time-transgressive record of silicic volcanism interpreted to be the result of movement of the North American plate over a stationary mantle plume. The second piece of evidence, still quoting, is the 4 zones of increasing seismic activity that form from the Intermountain seismic belt around the current location of hotspot activity. Finally, the third quoted piece of evidence is topographic changes resulting from the passage of North America over the hotspot.
Let's start now by considering the present topography in relation to the geological history of the Snake River Plain. The SRP, as we'll call it, has the shape of a broad V. It can be divided into 3 sections: western, central, and eastern. The western plain is a large tectonic graben filled with sediments that are underlain by rhyolite and basalt. The western plain began to form around 11 to 12 megaannums ago with the eruption of rhyolite lavas and ignimbrites, with several nested calderas below. The volcanic fields are progressively younger, moving toward the northeast, which nears and approaches the Yellowstone hotspot. The hotspot first appeared during the Middle Miocene, approximately 17 megaannums ago. Basin or range extension thinned the crust, allowing basalt magma, which melted from the mantle lithosphere boundary by the hotspot, and reached the surface, producing basalt lava fields across the Snake River Plain. For example, the Craters of the Moon National Monument. Glacial erosion of central Idaho mountains and the Yellowstone Plateau produced a great amount of silt carried by meltwater streams to the Snake River Plain. During low flow periods, winds blew the silt eastward, forming the Less deposits, which provide soil plentiful in nutrients for Idaho potatoes. Current studies suggest that the entire SRP resulted from the passage of the North American plate over a slightly migrating mantle plume or hotspot located beneath Yellowstone National Park. The North American plate migrates at a rate of approximately 4.5 millimeters per year over the hotspot, which shows substantial movement over geologic timescales. A dome-shaped topographic high moved northeastward ahead of the hotspot. This elevated bulge was inflated by hotspot-derived thermal energy. As the highland moved northeastward, drainage flowed radially away from it, mainly to the south, north, and east. As the bulge subsided, the west-flowing Snake River captures drainages like the Port Neuf and Big Lost rivers, and the SRP formed. The movement of the bulge also caused the continental divide to migrate eastward. Erosion shows evidence of flood in the form of abandoned channels, spillways, cataracts, and scabland identifies the floodplain between American Falls and Twin Falls. And the canyon farther west is strewn with huge boulders, some of them more than 10 feet in diameter, which are heaped in enormous bars of boulders and sand that rise nearly 300 feet above the canyon floor. Let's consider the potentially devastating eruption of the Yellowstone caldera. Such a giant eruption would have regional effects, such as falling ash, which could be heavy enough to collapse roofs, crushing inhabitants, and short-term, like years to decades, changes to the global climate, and in the worst case, potentially killing off all animals and bacteria over a great swath of the earth. Not really that big of a deal, depending upon the size of the magma chamber, that is, and how long eruption occurs. Such eruptions usually form calderas, broad volcanic depressions created as the ground surface collapses as a result of withdrawal of partially molten rock. Thanks to earthquake data given by geophysicists, seismic X-rays of Yellowstone's magma chamber show 5 miles down is the top of a massive chamber of magma trapped within the crust of the earth. This chamber is 25 miles wide and 50 miles long. In other words, the magma reservoir has an area larger than the state of Rhode Island. It is also the source of Yellowstone's geysers and quakes, with several thousands of tourists migrating to it yearly. The magma source to the chamber comes as a massive plume of heated rock extending 400 miles below the surface in the mantle. Partially molten rock is as little as 5 miles below the Yellowstone Park, with areas that are like 2 fingers of magma that are aimed toward the ground surface. The heat from these fingers causes overlying land to uplift in 2 large bulges. These bulges resemble hills and are called resurgent domes. The Sour Creek Dome is near the northeast side of the caldera, and the Mallard Lake Dome is near Old Faithful. I'd like to reinforce the point that given Yellowstone's history, the yearly probability of another caldera-forming eruption is approximately 1 in 730,000, or a very small percent against. I would also recommend seeing the documentary Supervolcano at topdocumentaryfilms.com or even YouTube. And that's it. This is the Snake River Plain.